Now we'll take a look at what happens inside the .git folder, and we'll dig a little deeper into how Git stores information and how this can help us with our work. In reality, everything in Git is built on graphs. This means that Git itself uses the hash function sha1 to process a file, and depending on the contents of the file, generates some kind of code, a string that will represent the hash of a specific object. Let's take a closer look at what that looks like. Let us simply open the .git folder and take a peek at what's inside. Here it is. It is called .git because in Linux and similar systems, the files and directories that begin with a full stop are hidden in order to not get in the way of anything. Let's go inside and see what we got here. In the hooks, there are scripts, but we are interested in the folder objects. The data that we commit to Git somehow makes its way into these directories and ends up in these objects. What interesting things can we find here? A very important file, the file title head. Let's open Notepad and see what's in there. Head contains some link to some object in the directory refs heads master, which is already indicating that we are currently in the master branch. Let's see what else is there. Refs heads, refs remotes, refs tags. In refs heads master, we can see that this is where the sha1 key is located, which means the 40 digits in the hexadecimal notation, which represents the result of the hash function sha1 involving some file. What's so interesting about this number? Let's open Git and call git log. Look here, the most recent commit starts with 63b9. If we go back to refs heads master, we can see this is the exact number, the hash that this link references, which means that our head pointer is placed on the last commit. This is normal behavior for Git. Usually the head points to the last commit. For the matter, it's even defined as a head. And with Git's help, we can switch to any other commit, and then the head will change. As soon as I create a new commit, the head changes, and refs heads master will include a pointer to the new commit. What else is in there? Inside there are remotes. These are the addresses, the commit states that are located in the remote repositories. Ours are currently matching because we already performed fetch and merge, meaning the state of our remote repository and local one is the same. There's also this interesting file index, which stores the transitional information that we are planning to commit. When we perform the operation git add, Git places the files in the transitional index and keeps them there until we commit them. Some more things we can see, there are config, description, and other configuration related things. The most exciting stuff is located here in objects. So what's in there? In order to understand what is inside, we need to figure out how exactly Git stores objects. In Git, everything is built on graphs, and the three fundamental object types in Git are the commit, the tree, and the blob. Blob is an abbreviation that means binary large object, and this is the minimum atomic cell of information storage in Git. Every commit can contain files that were changed, as well as directories that store these files. So the commits basically reference the trees, and the trees are used to define the names of the files that we're committing, as well as the names of directories that store them, which are the file paths. Let's say commit number 1 references one single tree that contains the name of the file song.txt, and at the same time it references a blob called ABB54, which stores the contents of the file, which means the contents of the file and its name in Git are stored separately. Trees reference blob files. A single tree can reference many blobs, and several trees and reference the same blob. Let's say if we're editing the song lyrics into commits, then if we're committing the same song with the same hash, then it's quite likely that Git will simply duplicate the pointer, meaning Git will not create a duplicate of an object. In the exact same way, every commit references the previous one, apart the very first commit, which has these references set as null. Let's see, using the commands listed below ls3 and show, how we can view the details of what exactly we have committed during the previous video trainings. Let's start by opening Git bash. I'm actually really excited about digging deeper in the contents of this commit right here, the very last one I did. Let's select the command git show, add a few flags, and then I will start simply inputting the first symbols from the SHA1 code of the current commit. Since I don't have many commits, 5 symbols should be more or less enough. Okay, what do we have? We can see slightly more detailed information about this commit. This means we can see more than just the commit and the author. We can also see the tree, which means we see the tree that this specific commit references. Let's go further and pick this tree apart. The command is ls3, and I similarly specify the few starting symbols from the SHA1 code. Okay, now we can see that this tree is located in the commit, meaning the commit references one tree, and that tree references two blobs, two separate binary large objects that have separate SHA1 codes. Let's take a look at the one that we modified. Let's look at song.txt. To do that, we once again call the command git show without any additional flags, and we start typing the first value. Okay, now we can see what is essentially a replica of the given file. When Git calls the hash function SHA1, it goes through the entire contents of the file, and as a result of the hash function, we can see the name of the blob, and the tree contains the data on how the file is supposed to be named, which means in this specific block we can view the content. So we need to get to the very bottom and see what exactly is inside of Git. Now let's note some interesting. Look, we have a blob that starts with 612179. Let's find out it on the disk. So here's what's interesting about it. Git doesn't create blobs exactly as they are written, exactly matching the SHA1 that they have. So in order to lower the load on the file system, the first two numbers in any object, regardless if it's a commit or blob, they create a directory. If we're looking for an object that starts with 61, then those first two symbols will be the name of the directory, and the rest of it, meaning the remaining 38 digits, will be the actual name of the file. I need the file from the directory 61 with the file name 2179. If we open it with Notepad, we will see the binary content. This won't do any good, but this is exactly why we have this command git show. If you want to play a prank on someone, you can rename the files and folders in this directory here, and it will be very, very difficult to track the problem, and they will most likely be forced to clone a new repository. What I'm trying to say is that it's best to stay out of here. I know very few real situations that would require performing some operations directly in .git directory. As a rule, everything is done via the command line